So these are practice exercises from a couple of different pages in the textbook where we're going to practice naming and then writing formulas for ionic, covalent compounds, and then acids. So first thing we're looking at is naming some ionic compounds. We can tell that these are ionic compounds because they are made up of cations and anions. Remember that cations always have a positive charge and anions always have a negative charge. So what I like to do with these problems is I like to identify where the cation is, where the anion is. So in the first one, I can split it there. You should recognize the ammonium cation. That's a polyatomic ion, one of the ones you should have memorized, and that has a charge of +1. And if you don't know that, you can look that up in your textbook. On the right-hand side, that's my anion. That is the bromide anion that comes from bromine, and I can tell because of where that is in the periodic table, it's in group 7A, that it has a charge of -1. So when I write out the name for this, I just list what's there. We don't use any prefixes in ionic compounds. I've got ammonium, bromide. Notice that this is not ammonium bromine. I changed the INE ending to IDE. So ammonium bromide. So the next one, again, this is an ionic compound, cation and an anion, and typically ionic compounds are going to have a metal and a nonmetal in them. So again, I can split this in half here, and we should see the chromium is the metal and oxygen is the nonmetal. So what happened in A with the ammonium bromide? All of those are nonmetals. Well, the ammonium polyatomic ion is a strange polyatomic ion in that it's made of only nonmetals, only nitrogen and hydrogen, but it still has a positive charge. So that is an ionic compound that does not contain a metal. That's a special circumstance that you're going to want to watch out for. So most ionic compounds will have metals in them, but that's not 100% accurate. All ionic compounds have cations and anions. And again, ammonium is a strange cation in that it's only made of nonmetals, yet still has a positive charge. So back to part B with my chromium and my oxygen. So if I take a look at chromium in the periodic table, chromium comes from the transition metal portion of the periodic table. And you should remember that with transition metals, we don't always know their charges. So in order to determine the charge on this chromium, we're actually going to work backwards from the charge that we do know. We should know the charge on oxygen because oxygen is in group 6A. That means it's going to have a -2 charge. But if you look, I have 3 oxygen atoms. So if I've got, for the oxygen, a 2- charge, and I have 3 of them, that means I've got a total charge of -6 for my anions. So if I've got a total charge of -6 for my anion, that means that my cation must be +6. Because in order to make an ionic compound, the charge on my cation and my anion need to cancel. Well, I know I've got 2 chromium atoms, so what times 2 equals +6? That should be obvious that +3 times 2 equals +6. So what this means is that my chromium has a charge of 3 positive. Again, since this is a transition metal and you don't know the charge just by looking at it in the periodic table, we use the name to help you figure it out. Specifically, we use Roman numerals. So I would write this as chromium 3 oxide. Notice that that 3 is a Roman numeral and it's chromium 3 oxide. The 3 does not tell me how many of anything. The 3 tells me that my chromium had a 3 positive charge. Let's go ahead and look at the next one. Again, we should be able to split it in half, find the cation and the anion. In this case, the cation is cobalt, another transition metal, so I know my name is going to have a Roman numeral. My anion is nitrate. This is a polyatomic ion that you should have memorized, or you can look it up in your textbook. That polyatomic ion nitrate has a charge of -1. But you should notice that I have 2 nitrates to balance out the cobalt. Well, if I need 2 nitrates, that means that the total negative charge here is -2, so the total positive charge must be +2. This tells me that my single cobalt atom has a 2 positive charge, and I have 2 nitrate anions, each with a -1 charge. So when I write out this name, it's going to be cobalt 2 nitrate. Again, the Roman numeral 2 belongs to the cobalt. It is telling us the charge on the cobalt ion. It has nothing to do with any of the numbers in the formula. So the Roman numerals always tell you a charge. They don't tell you how many atoms. So cobalt 2 nitrate. And again, you only need Roman numerals with transition metals. Any other metal from group 1A or 2A, you know the charge because of where it is in the periodic table, so you would not use Roman numerals. Okay, let's try working backwards. Now that we have names, let's try to give formulas. So the first one, we're telling us magnesium sulfate. So again, you should be able to figure out where my cation and my anion is. I can tell that this is an ionic compound because it's got a metal and a nonmetal. I can use my periodic table to look at magnesium. Since magnesium is in group 2A, that means that it has a charge of +2. Sulfate is a polyatomic ion that you should be able to look up, and sulfate has a charge of -2. Since these charges cancel, I've got a +2 and a -2, I can just write them out. So magnesium has the symbol Mg, and that sulfate is SO4. Notice that when I write the formulas, I do not write the charges in, because the whole point of writing an ionic formula is so that the charges cancel. Let's look at the next one. Silver sulfide. Again, we should see the metal and the nonmetal. Silver has a +1 charge, and sulfide, so sulfide means that it's just sulfur, this has a -2 charge. Look at the difference here. The IDE is just sulfur, the ATE has oxygens involved. So when you see ATE, you should be thinking oxygens. Now when I write the formula for silver sulfide, silver has the symbol Ag, and sulfide is just S, it's just a sulfur. But notice the charges did not balance. Silver was +1, while the sulfide was -2. This means that I need 2 silver atoms in order to balance the charge on the sulfide. Remember that I write the number as a subscript, and it goes after the atom it applies to. So Ag2S means 2 silver atoms and 1 sulfur atom, silver sulfide. Next one I'm looking at is lead nitrate. Again, I can tell this is ionic because I've got a metal, that's lead, and a nonmetal, that's nitrate. And they've given me a clue here. Notice the Roman numeral. The Roman numeral 2 after lead tells me lead has a charge of +2. Nitrate is again a polyatomic ion, something you should know by looking it up, and nitrate has a charge of -1. So when I put these together, I write the symbol for lead, and I can write the symbol for nitrate. But again, they don't balance. The 2 positive charge on the lead does not cancel with the 1 negative charge on the nitrate. I need 2 nitrate groups in order to cancel the charge on the lead. In order to tell you I need 2 nitrate groups, I'm going to put them into parentheses so you can see that there are 2 of the entire group. So with polyatomic ions, you have to keep the group together. Okay, let's look at the next set. In this case, we know we're dealing with acids, and it's very obvious when we're dealing with acids because the name ends in acid. So if you look at your naming rules, this first one is a hydrobromic acid. When you see the hydro in there, that means that there is no oxygen. Since I know that this is an acid, I know I'm going to have hydrogen in there, and hydrogen always has a charge of +1 in an acid. Bromic comes from bromine, and if I look on the periodic table, bromine is in group 7A. It's a halogen, so it's got a charge of -1. Those charges will cancel. +1 on the hydrogen, the -1 on the bromine, so hydrobromic acid has the formula HBr. Again, no oxygen there. If I look at carbonic acid, that ic name means that there is oxygen, and specifically ic means that it came from the carbon 8 ion. Again, if you look at the rules in your textbook, the polyatomic ions that end in ate become ic with acid. If they end in ite, ite, they become ous when we write them with acids. And again, because this is an acid, I know that it's going to have the positive hydrogen ion, and I can write the carbonate ion. So carbonate again is a polyatomic ion, CO3 with a 2 negative charge. Again, that's all together. So thinking about these charges, one single hydrogen with a +1 charge is not enough to cancel the 2 negative charge on the carbonate. So I'm actually going to need 2 hydrogen ions. We write those in using subscripts. So carbonic acid is going to have the formula H2CO3 because I needed 2 hydrogen ions to cancel the charge on the carbonate ion. Again, notice with these acids, same as for the ionic compounds, you do not see the charges in the final formula. The charges are only there when I'm trying to figure out how to write it, but my final answers, which I'm going to circle, do not have charges. So the last set that I'm going to look at, these are a little bit different. So these are all covalent compounds, or molecular. And I can tell that because they are all nonmetals. So silicon is actually a metalloid, but that still counts with the nonmetals, so that's going to be a molecular formula. These, we should also tell they're a little bit different because we see prefixes, so tetra, di, and di. Writing molecular or covalent formulas is actually very easy. You don't have to worry about charges because they tell you exactly what to put in. So all I need to write in is silicon, which has the formula Si, and then I know I have 4 bromines. And again, those go in as subscripts after the symbol. So silicon tetrabromide, SiBr4. The next one, disulfur dichloride. The prefix di means 2. We know that sulfur has the symbol S, so there are 2 sulfurs. Chlorine has the symbol Cl, and there are 2 chlorines. Again, notice that the chlorine, the INE ending, changes to IDE in the name. So when it's made of sulfur and chlorine, it's called disulfur dichloride. So, what's different about the silicon tetrabromide and the disulfur dichloride is that I don't put a prefix on the first one if there's only one atom. I don't write monosilicon tetrabromide, I only use a prefix if it's greater than 1. So disulfur gets a prefix, but monosilicon would not. So again, those last 2 were covalent compounds, different from the other ones, which were ionic or acid compounds.